In this video, we're going to look at that mathematical convention that we talked about in class. We had done the no perfect square factors under the radical, but the two things we didn't talk about were the no fractions under the radical and no radical in the denominator. So again, this is just how mathematicians simplify radicals. It's how we want to write them. So it's not that if this happens, your answer is wrong. It's just not done. Okay, so the process we're going to go through is called rationalizing the denominator. And it's called that because what we're doing is making the denominator rational. So if I look at this example 6 here, because we're continuing the notes from Wednesday. If we look at our example 6 here, see this square root in the denominator? We don't like that. It's irrational. We don't want it to be irrational. So we are going to rationalize. And here's what we're going to do. And this is going to seem weird the first time we do it. I'm going to multiply top and bottom by the square root of 5. I'm going to multiply top and bottom by the square root of 5. The thing we need to notice is that that equals 1. So I can multiply by it without changing anything. I can multiply by the square root of 5 over the square root of 5 because it equals 1, and I can multiply by 1 without changing anything. Watch why I do that. Across the top, 2 square roots of 5. Across the bottom, square root of 25. Oh my goodness, that's a perfect square. If you're thinking, let's reduce the 5 and 25, don't do that. You're just going to undo the work we just did. So I'm going to take my square root there. Square root of 25 is 5. That's my rationalized answer. So this and this are equivalent to each other. They're equal. If I punch in 2 over the square root of 5, 2 divided by the square root of 5, I get 0.8944279191. And if I do 2 times the square root of 5 divided by 5, guess what I get? 0.8944279191, the same thing. This answer is better because it follows our convention of not having a square root in the denominator. So we have rationalized that denominator. Now, I chose square root of 5 over square root of 5 because I was trying to get rid of a square root of 5. If this had been a square root of 7, I would have done square root 7 over 7. Okay? Here, if you're thinking, oh, let's reduce those 5s. This one's under a square root. This one is not under a square root. They don't play together. I could reduce these, except they have no common factors, of course. So let's do one more example, and then we'll continue working some in class. Example 7, we have the square root of 1 over 8. Now, the convention that this one is not following for us is that I've got a fraction under my square root. So I'm going to start by separating them out. That's my quotient property that allows me to do that. It's actually your exponent quotient property, because square roots, we're going to find out, are really exponents in a really weird way. Then the square root of 1 is 1, and 8 has a perfect square hidden in there. 2 times 4, so the square root of 4 is 2, and then that 2 gets left behind. I want to make sure we understand where those numbers are coming from. The square root of 4 is 2, and then this 2 is right there. I probably should have chosen something other than 8. Okay, now, the thing I don't like is that square root 2 in the denominator. So you know what I'm going to do? I'm going to multiply top and bottom by square root 2 over square root 2. I can do that. That is legal because it's equal to 1. So in the top, 1 times the square root of 2 is square root 2. In the denominator, I'm going to get 2 times the square root of 4. I can multiply those. Those are under the square root together. And then the square root of 4 is 2. And then finishing it off, I get square root 2 over 4. So in this case, this and this are equivalent. Again, you can't reduce that 2 and that 4. One's under the square root and one is not under the square root. So you can't reduce them. And we will continue working on these as we do our solving using taking the square root.